Like if you were to write, like if you want to write out the factorial, it just doesn't make any sense.
Okay.
Right.
Are we ready? All right. So, if I give you the equation of the sequence, deciding of it if it converges is not bad. Right? What if I just give you the sequence? Then you need to be able to define the sequence. All right. And so we could look at this and we try to define the sequence as 2, 1.33, 1.6, whatever that works out to be, 1.2, 2.28, give or take, etc. You guys get what I'm trying to do here, yeah? Okay? I don't recommend that we do that. Instead, if I want to define a sub n, what I'm going to do is define the top and define the bottom. Okay, so what are you guys noticing about the top? It's doubling. And in fact, this is 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. So really, the first two, A1 is 2 to the 1, A2 is 2 to the 2. So my numerator is 2 to the whatever power I have. Is everybody good? And then my bottoms are increasing by 2 each time, right? So that's a slope of positive 2 constant. So 2n. And then what does my rest of my term need to be so that it matches? Minus 1. 2n minus 1. And to kind of help you guys through. So you know it's 2n something. And I know my first term for that something has to equal 1. So I need to subtract 1 from that. And 2 times 2, something's got to give me 3. That's how I get that number. Is everybody okay? So in terms of defining my sequence, especially if what we have are fractions, my suggestion to you is that to define it, you're going to look at the top and the bottom separately, the numerators and the denominator separately, okay? Now that we've defined our sequence and we want to decide does it converge, we're going to take the limit as I'm going to an infinite amount of terms. Is it equaling a whole number, or is it equaling a finite number or not? Okay, so I'm going to take the limit as n goes to infinity of my defined sequence. If I try to take that limit right now, it's infinity over infinity. So L'Hopital says I can take the derivative of the top, 2 to the n ln 2, derivative of the bottom, so this sequence diverges. Everybody good? Okay, let's define this sequence. This one is not as easy to see. So what's the first thing you might notice about this sequence? It's what I would call alternating. Okay, we have something called an alternating sequence. Oscillating, same idea. Okay, it's positive, it's negative, it's positive, it's negative, it's positive, it's negative. So I know from the very, very get-go that my a sub n is going to have a negative 1 to a power. And I got to decide, is that negative 1 to a power n, is that power either n or n plus 1? Is everybody with me? And the way I decide that is when n equals 1, I want it to be what? Positive or negative? negative. So I'm going to do negative 1 to the n power because it's starting on a negative term. And if I plug in 1 for n, I've got negative 1 to the 1 power, which is also negative. Then when I plug in 2 for n, this term becomes positive. Is everybody good so far? Okay. Next, we got to see, well, what's going on. You guys want to do the top first or the bottom first? Top. Okay. So let's try to outline some things that we're seeing here. What's one? So you no longer have to worry about the positives and the negatives. We're just looking at the overall magnitude of the numerators. What's happening to my numerators? Let's start with increasing or decreasing. Increasing. Okay? All right. So for this one, it went up by 6, right? For this one, it went up by, I think that's 18. And this one, is that 54?
Yeah.
And let me see if I can guess the next one. I'm not even going to look at it yet. I bet it's 162. What are you noticing about what it's increasing by?
Each margin is multiplied by 3.
The margin's being multiplied by 3. When that margin's always being multiplied by the same number, it's going to be something like 3 to a power. If I'm multiplying by 3 over and over and over again. Is everybody with me so far? Okay, now. For if n is equal to 1, right? What's the value of 3 to the n? 3, yeah? If n is equal to 2, what is the value of 3 to the n? 9. What are you noticing?
1 less.
It's 1 less each time. What's 3 to the third? 27. Is everybody good? Are we seeing it? Okay, so my numerator is going to be 3 to the n minus 1. Now, let's talk about my denominator. What's going on in my denominator? It's increasing. So we could say it's going up by 1, then by 4, then by 18, and then by 96. That's not helpful to me. I'm not seeing any pattern in how it's going up by. So after I try the addition, it's not working well for me. I'm going to try multiplication next. Times 2, times 3, times 4, times 5. And we can see that the denominators are n factorial. The numbers of factorials, like the 1, 2, 6, 24, 120, those are going to start feeling real comfortable for you. Like we're going to use them a lot. Okay? Is everybody good? I'd like to say we've done the hard part. Because defining the sequence, this was not an easy sequence to define, right? Okay. But now we also have to decide what is the limit as n approaches infinity of negative 1 to the n and some of you might be saying, we can tell right away that this is oscillating, right? Or it's alternating, so there's no way it could converge. Except for we have a slight problem, okay? Because alternating, imagine I'm taking this limit and I'm alternating from positive to negative to positive to negative to positive to negative to positive to negative. It could still converge if it's converging to 0. Is everybody seeing this? Okay, so we have to be really, really careful. Just because it looks like, just because it's alternating doesn't mean it doesn't converge. So what we're going to do is we're going to take the limit, and the only way an alternating sequence converges is if it converges to 0. So what we're going to do is we're going to ignore this part. Okay? But in the back of our heads, sorry, Riley, we're going to ignore this part. But in the back of our heads, like if it's alternating around 0, but getting closer and closer to 0, the limit still exists. Are we all on the same page here? Okay? So let's ignore this and say, does this limit equal 0? And the problem with this is, what is the limit? Like this limit is infinity. I agree with that. The limit of the numerator is infinity. What about the limit of the denominator? Just thinking through, it's going to be infinity. And so now we have this L'Hopital's form, but the problem with thinking about this one through L'Hopital's form is, I don't know. Guys, I'm pretty learned at taking derivatives, and I don't know how to take the derivative of a factorial.
Is there like knowledge or is it just?
I don't know. I've never been taught if there is one or there is not one. It's hard because of the continuity. The factorial, I don't believe, is a continuous function. Okay. So real quick, if I took the limit of n, as n goes to infinity, of 3 over n, are you guys with me that that is equal to 0? Okay, and if I ask you, why is that equal to 0? It's because the bottom is getting bigger faster than the top is getting bigger. Is everybody with me? Okay. So as n goes to infinity, every time I have an n here, if I ignore that minus 1, okay? Because as you guys can look, that minus 1 comparing, say, 242 to 243, that minus 1 is not really affecting the top very much as n's getting really big. What's the difference between, say, 242 and 243? The next one is 728 to 729. That minus 1, as n is getting really big, that minus 1 is pretty inconsequential. Okay? So as n is getting bigger, the top's getting multiplied by 3 over and over and over again, right? As the bottom is getting bigger, as n is getting bigger, the bottom is getting multiplied by a lot bigger than 3. Is everybody good? So as I'm looking at this, yeah, it's infinity over infinity, but from as n increases, the numerator is being times by 3. Then by 3, and then by 3, right? Whereas my denominator, if I keep this going, times 6, then times 7, then times 8, my denominator is rising a lot faster than my numerator. So for large values of n, I'm going to have a smaller number on top and a bigger number on the bottom. And that's going to continually happen. Okay? So this limit is equal to 0. So this series or sequence converges even though it's alternating. And when we get to something with, say, a factorial versus an exponential, that factorial, exponentials will multiply by the same thing over and over and over. Whereas factorials, we're multiplying by a larger and larger and larger, so factorials rise more quickly than, yeah.
Could we have done this in the past instead of L'Hopital's? I feel like there are a lot of times where you could have said the top was greater than bottom.
Yeah, So I think there's some special cases in this particular case because n is a positive integer, right? Like there's the nuance of this. It's a little bit more nuanced when you're talking about continuous functions, but yes, it's the same reasoning. And in fact, the reason L'Hopital works is what are you doing? You're basically finding rates of increase. It's actually kind of a proof for L'Hopital.
Right.
And L'Hopital is useful when you're getting to functions that's hard to tell which one's rising faster or smaller. But yes, it is the same reasoning for sure.
The calculator can't derive a factorial.
I tried that.
I think the continuity would cause a decent amount of problems because factorials are definitely discrete, right? Like there is no in between one factorial and two factorial.
If you do the derived function in sequence mode, it doesn't.
How are we feeling? Okay. All right. The last thing for sequences is what we call monotonic, or is a sequence monotonic, which interestingly is monotony, but okay. And a sequence is monotonic if it is all increasing or all decreasing. And so if we're trying to decide it, the very first thing I would do if I'm trying to decide is a sequence monotonic is go by inspection and just figure out what are the first few terms of the sequence. Okay? So like if I'm looking at this one, A1 was 2, I think, right? This is the same sequence we've been dealing with, so it's 2 and then 4. And the minute I get to this, so here it was increasing and now decreasing, this is not monotonic. And I would point out that, and if I go down to say this one, A1 is 1, A2 is 4/3. So to get from 1 to 4/3, which by the way is 1.33, right? To get from 1 to 4/3, that's increasing. A3, this is the one we did the other day, y'all, would be 9/7. And so there we're decreasing. And again, I'm going to say for sure this one is not monotonic.
Is there a word like polytonic for that?
Sure.
Polytonic.
Bitonic?
Polytonic. Okay.
Sure. If there is a word, I've never heard it, but If we want to decide as a group that not monotonic is polytonic, I'm fine with it.
I'm ready now.
I won't accept tritonic, though. Well, actually, it could be tritonic.
What's
'Cause
the
it could
tonic-
increase-
What's the tonic mean?
I think it's direction.
Yeah, okay.
So it could be up, down, or
Level.
Right.
Yeah.
So it could be tritonic. But what kind of sequence would you have where two of the terms are the same?
Oh, I'm sure I could come up with
in
one.
sequence? And then you also have increasing and decreasing.
And equals 2.
It'd just be like
changes what you're saying.
that.
Right.
That's not that hard to
Uh,
right now.
well, that seems like a fun game for me to do later today instead of real work. Okay.
Sequence where you have
So
two numbers in a row.
all right. So let's look at this one next.
At some point.
Because one of the things I'm going to ask you to do is prove that a sequence is monotonic. See, you guys mess me up all the time. Monotonic, okay? And so if I start this one by inspection, right? If I do A1, let's see, we get -1, right? A2 would be 2 minus 1 over 2 times 2 is -2/3, yeah? And then A3 be 3 over 1 minus 2 times 3. negative 3/5. And just because, again, we're trying to think about increasing and decreasing, this is negative 0.67, and this is negative 0.6. It'd be 4 over 1 minus 2 times 4, so negative 4/7, which is, again, I have my cheat sheet, so on inspection, if for my first few terms, okay, for my first few terms, it appears to be monotonic. And a nice teacher would say that's good enough. I'm not nice. Okay.
Very intimidating.
This is my scary face. All right, so here's what we're going to do. If we can show that for 2 consecutive terms, one is always the top, for 2 consecutive terms, so by the way, those 2 consecutive terms are like AN and AN plus 1, right? That's how you would describe 2 consecutive terms. If we can just show that algebraically one is always larger than the other, then we can show that it's monotonic, okay? Yeah.
I get that this wouldn't work if you have a factorial, but could you take the derivative of it and then see if there are any, like...
See if the derivative's
zeros?
always positive.
Yeah.
Yes, you could. One approach that I tried with one that I was really struggling to show was, in fact, I have pages on pages of that over there, is that you could do, like, that was one of the approaches I showed, and then the derivative was not always positive nor always negative. And remember, we're only doing this for values of n that are greater than or equal to 1. Okay? All right. Now, the first approach I'm going to show you is to look at the values of AN plus 1 over A sub n. Okay? Now, like I said, if AN plus 1 is always bigger than A sub n, that would suggest always increasing, yes? If the value of the next term is bigger than the value of the first term, okay? So we can look and say, is this fraction bigger than 1? And if this fraction is bigger than 1, then the sequence will always be increasing. Is everybody good? Okay? And likewise, if AN plus 1 over A sub n is less than 1, then the sequence would always be decreasing. Because the top would be bigger than the bottom. Wait, I said that backwards. Is everybody good? And what happens, so if we can show that for n greater than or equal to 1, either of these to be true, the sequence is monotonic, and if we can show that it's equal to, like if we can't show that, then it's still inconclusive. Okay? We ready to look at one? Okay, so what would, in order to find AN plus 1, I'm basically going to replace all the n's with n plus 1. So I'm going to do n. Are you guys comfortable with me calling that negative 1 minus 2n? Like doing my distributive and combining like terms? Is everybody cool? Okay, so I'm going to do n plus 1 over negative 1 minus 2n. That's my an plus 1 over n over 1 minus 2n. Everybody good? We feeling comfortable? And I don't know about you guys, but this looks icky to me. Fractions within fractions, I don't like it. So I'm going to go ahead and multiply by 1 minus 2n over n to make my instead. We feel good about that. All right, now, since this is multiplying, I can change the order I write this, yeah? I can change the order I write my denominator, change the order I write my numerator. So I'm going to rewrite this as n plus 1 over n times 1 minus 2n over negative 1 minus 2n. Everybody good? And what do I know about n again? It's greater than or equal to 1. All right, if that's the case, are you guys with me that this fraction is always bigger than 1? What about this one?
Yes.
This one's also always going to be greater than 1 because the numerator is always going to be larger than the denominator. So what can we say overall? If a number bigger than 1 is being multiplied by a number bigger than 1, the whole thing is bigger than 1.
And when do we have to do this as opposed to just analyzing?
If I ask you, is it monotonic or not, you actually need to prove
Okay.
that it's always increasing or always decreasing. This gets you there.
Okay.
Everybody good?
What if we can see in the first couple ends that it doesn't do that? Do stop at the-
Yeah, so like that's why I said I would always start by inspection. Like here we didn't do this because it was very clear. Like you can use like by inspection at the very, very beginning. If you can show in the first couple terms that it increases and then decreases, proving something is not monotonic is a lot easier than proving something is monotonic. You feeling good? All right, so let's look at this one. An plus 1 would be n plus 3 over n plus 1 factorial. So my fraction would be n plus 3 over n plus 1 factorial over n plus 2 over n factorial. And like I said, I like to jump really quickly into that. Whoop. Flipping that denominator and multiplying, it makes it a lot easier for me to see what's actually happening here. Oh, you guys, if you did this by inspection, it is always decreasing. But the first few terms are all decreasing. Okay, so right, so I have n factorial over n plus 1 factorial. It's usually pretty useful. It's usually pretty useful to
So what?
to put the like pieces together, right? Like to put the factorials into one fraction. Why is that easier? What can I do about n factorial over n plus 1 factorial? Yeah, the factorials basically could cancel, like in the same, like we did it backwards 2 seconds ago, right? Okay. So now I have n plus 3 over n plus 1 n plus 2. And can we say that this is always greater than 1 or less than 1? So I might call that n plus 3 over n squared plus 3n plus 2. Okay? I might look at that just to be real clear on this. Certainly for large values of n, the denominator is going to be much larger than the numerator. And then we say for the small values of n, like n equals 1, the numerator is smaller, and as they increase, right? But I would be comfortable with you saying that this is less than 1 for all n greater than or equal to 1. So this is in fact monotonic. And monotonic decreasing since it's less than 1. This would be monotonic increasing because it's greater than 1. I never wrote that part down. All right, this is a good breaking point. Let's take we'll 2 to the 2. All right. Series and convergence. All right. So here, here's a sequence 2 over n squared. If I asked you guys, could we figure out this one? I'm calling b sub n. I don't know why I chose b instead of a. Whatever. If I asked you, could we figure out each term of this sequence? Like, so b1 would be 2 over 1 squared, which is, I think, 2. I'm not very good with numbers, though. And then what would b2 be? One half. b3 would be 2/9. b4 is 2/16, which I'm going to call 1/8 if you guys don't mind. 2/25, etc. Okay, so we have this is the sequence. S sub n is the sum. Okay, so S1 and B1 are going to be the same value. Okay, but S2 is going to be the first term plus the second term. Because it's the sum of the first 2 terms of the sequence. And then S3 would be that value plus B3 because it's the sum of the first 3 terms of the sequence. Okay? In Richard's class, we also wrote this as, for instance, the sum from n equals 1 to 3 of 2 over n squared. Do you guys remember doing sigma notation a really long time ago? And when we do that sigma notation, this is saying which 2 terms are being, or which terms are being added together, A1 through A3 of this sequence. And this I think it's math 0. I'm pretty sure that's what you kids are doing right. I'm pretty sure it's math 0. You can actually fill the sigma notation in. And as long as you're doing these ones, so S4 would be the previous term plus the previous sum plus the most recent plus the 4th term, because now you're talking about the sum of the first 4 terms of the sequence. And you get 2.847, etc. Right? And this one ends up being 2.927. And all of these are different partial sums, because they are a sum of part of the sequence extending on to infinity. Okay? And in Richard's class, you only dealt with partial sums. The bulk of this class, and where this class is going to start to extend, is we're going to start dealing with the infinite sums, or the infinite series defined by this sigma notation, where now I'm not having 3 terms or 4 terms or 8 terms or however many terms you want. I'm having an infinite amount of terms. Is everybody good? All right. Certainly the one in your calculator, you can't plug in infinity, right? So Every good so far? All right. So just like a sequence, a series can converge or diverge. So the sequence converged when the limit was finite. The series converges if the series has a finite answer. Okay? And the bulk of what we're going to be doing in the homework packet is deciding, does a series converge or diverge? Okay? And there's lots of different rules depending on how that series is defined. Okay? So, 1 minus. So, in order to to work through this, so the beginning of this, to find our series, let's start with listing our first three terms. So, because in order to get our first three partial sums, we're going to want to look at what are our first three terms. All right, so my first term, if I plug in 1, is 1/2. So my first series, or my first partial sum would be 1/2, okay? Now, what is my second term of the sequence? In other words, what is A2? It would be 1/4. So S2 would be 1/2 plus 1/4, which is 3/4. And A3 would be, I think 1/8, yeah? And what would that make S3? 7/8. What are we starting to notice? Ooh, approaching 1, maybe. What else are we starting to notice?
Top is 1 less than the bottom.
The top is 1 less than the bottom. Okay, so in order to do this like approaching, okay, what we want to do is we want to be comfortable with taking a limit of something. In order to take a limit, we need an equation. Okay? And are we comfortable that the top will always be 1 less than the bottom? Well, let's think this through real quick. If I try to do S4, so A4, of course, becomes 1/16, right? If I'm doing 7/8 plus 1/16, right? That becomes 14/16 to actually add those together. Right? And whenever I get that common denominator, this is going to be 2 less. Right? Is everybody with me? Once it's true for that one, and then I'm adding 1 on top of that. And it's always going to be 1 because of the way my sequence is defined. So I am now comfortable, like as I'm thinking through this process, it is always going to be that to get my common denominator, I'm going to multiply by 2, which makes this 1 less here, 2 less, and then I'm adding 1, so it's 1 less. Okay? So, All right. So now if I ask you what is the equation for S sub n, basically what I'm doing is, it's now each of these partial sums are in themselves a new sequence. Is everybody with me? So how could I define that sequence? Well, let's start with the denominator. What's the denominator? 2 to the n, because it's doubling each time, which makes my numerator 2 to the n minus 1. And now Alex said, hey, it's approaching 1. now I have a sequence that I can say, is it approaching 1? Well, let's take the limit as n is approaching infinity of 2 to the n minus 1 over 2 to the n. This is one that I'm very comfortable calling a L'Hopital form, right? When I take the derivative, remember how I said when your n is getting really big, this doesn't matter? Really, it doesn't matter because when I take that derivative, it's going to go away, and now my numerator and denominator are the same, yeah? Is everybody good? So, the limit as n goes to, we're going to take those derivatives. 2 to the n ln 2 over 2 to the n ln 2 is equal to 1. So we can say that this series converges. Everybody good? All right. So if I'm doing 2 to the n, and I'm doing my first three partials, if I'm finding my first three partial sums, I'm going to find my first three terms. 2 to the 1 is 2, 2 to the second is 4, 2 to the third is 8, yeah? So S1 would be 2, S2 would be 6, S3 would be 12. No, I lied, 14. Anyone got a rule? Two.
2 to the 2n, then minus 2.
I don't know. I did it wrong when I did my notes, so I found a sub. I used a sub n instead of s sub n. So let's see.
No, because then you're
Yeah, no.
the second one doesn't work.
It's plus 4, then plus 8.
What's the fourth one?
Yeah, see this is how I would have to do it, and so S4 would equal 30.
16. Okay, so that seems significant. So we're adding.
Yeah, I mean we're doing.
I mean, yeah.
Of course we're at yeah.
But like.
So our sequence is 2, 6, 14, 30.
Wait,
So this
2
is.
times 2 to the n minus
I think
2?
it's. So this is
Instead of
4
2.
minus 2, 8 minus 2,
What do you say?
16 minus 2, 32
Yeah.
minus 2. I think it is 2 to the n plus 1 minus 2.
Oh, that's different from
Am I right? That's
But Landon uses the same
what does it work?
Yeah.
like this is 2 to the 5th, 2 to the 4th, 2 to the 3rd, 2 squared.
No, here's the
2 times, yeah, that's the same thing.
It is the same.
2 times 2 to the n, if you add your exponents, is 2 to the n plus 1. It's the same
Yeah.
thing. Remember when I said there's all sorts of rules to help us figure out if something converges? There's one for this that we're going to learn on Friday. Okay? So you're not going to have to, you will not have to get to this, I don't think. Maybe in your homework, but probably not. Okay? And besides, overall, guys, is this series going to converge or diverge? It's going to diverge because what's happening to my value? My limit is definitely not going to be a whole number. Or is not going to be a number. It's definitely going to infinity. And it's going to infinity quite quickly. Do you guys want to do the telescoping series today, or? Telescoping series are kind of fun. I think you guys will see why we call this a telescoping series as we do it. All right. So I'm going to kind of write this as S, okay? Because for this particular one, I think it makes sense to, we're just going to keep adding terms as we go and you'll kind of see it. So, you guys, what is A1 in this particular case?
1/2.
I'm going to actually write it as its two terms, okay? So it's 1 minus 1/2. So my first partial sum is 1 minus 1/2. Okay. What's A2? It would be 1/2 minus 1/3. So if I'm finding my second partial sum, S2, I'm going to take this 1 minus 1/2 and I'm going to add 1/2 minus 1/3. Now, what's A3? It would be 1/3 minus 1/4. And what are we noticing?
Cancel stuff out.
For a telescoping series, what happens is as I add in my new terms, I'm always canceling. And the way it works is when you have a positive and a negative, and that negative is going to become a next term. Does that make sense? Whether it's n plus 1 or n plus 2, it's going to work out that way. Okay? And so, in reality,
Less, yeah.
I'm saying if you stop, you can see it, but if it's moving, like if you keep going, well, if you stop. It's like how you can't know a particle's position.
Right.
You can't.
so some things,
As soon as you observe.
I would say terms are will consistently cancel as we add new terms in the sequence. I'm going to say, let's do it this way. Values consistently cancel as we add new terms to the series. That's the best way to describe it. And that's what we call a telescopic, because in reality, you kind of think of, when you think of a telescope, it kind of it nests inside itself, and it's almost like the outer rim of a telescope. You guys get what I'm saying here now, right? You can see kind of stretches out or condenses back down when you add it together, okay? So, because of that, in some capacity, in some capacity, S sub n in this case is 1 minus 1 over however many terms we're adding. I'm sorry, in this case it's n plus 1. Right? Because this was S1, S2, S3, S4. So it's A1. It's the start of A1. And then what the part being subtracted at the end is the 1 over n plus 1. Okay? And that's what we call a telescoping series. Okay. And y'all, telescoping series and the geometrics on the previous page, which you don't know are geometric yet, but the exponentials that we did on the previous page, okay? In some respects, we can come up with an equation that models the series. That the series itself is a definable sequence. Everybody good? And so when that happens, and you can take that definition of the series,
Shouldn't all telescopic series converge?
I don't think so.
Okay.
Because if this sequence was n minus n plus 1, if it was n minus n plus 1, that last term would be getting bigger, not smaller.
Oh. Yeah, okay.
So this limit equals 1, which it converges. Are we feeling okay? That is where I would like to stop today. Our more with series tomorrow.